Welcome to Math TV with Professor V. In this video, we're going to talk about inequalities in two variables. Now, we've previously shown the solutions of inequalities in a single variable, and we've done this by graphing them on a number line. We've also graphed equations in two variables previously, equations of lines specifically. So now what we want to do is display the solutions to inequalities in two variables on a graph. So first, let's stop and think, what would it take to be a solution to an inequality in two variables? So for example, let's determine whether the ordered pair 4, 2 is a solution to the inequality 2x minus 3y is less than 8. Well, to determine whether or not it's a solution, we're simply going to substitute in 4 for x and 2 for y and see if it satisfies the inequality. So let's see. Is 2 times 4, I'm replacing x with 4, minus 3 times 2, replacing y with 2, is that less than 8? Put a little question mark over the inequality because you're just not sure yet, right? We're still checking. So on the left-hand side, now we have 8 minus 6, that's 2. And yes, 2 is less than 8, that's true. Okay, so that means yes, 4, 2 is a solution. All right, you can't sit around and list out every possible solution to an inequality. There's infinitely many. It's just not going to happen. So the way we represent a solution set to an inequality is graphically. And we're going to begin the process of graphing the solution set to an inequality by first graphing the related equation. Okay, so here's how it works. We've got this inequality here. 3x plus y is greater than or equal to 5. To start things off, I'm going to consider the equation 3x plus y is equal to 5. So you just change that inequality to an equal sign, and we're going to graph this guy, okay? Most of the time when we're graphing lines, we like to put them in sloped-intercept form, meaning isolate y. So then now I can easily see, okay, the slope is -3, and the y-intercept is 5. So m, the slope, is -3. If you want to write that as -3 over 1, to remind yourself, that's the rise, that's the run, and then the y-intercept, remember, it's an ordered pair, it's at 0, 5. Okay, so let's go ahead, graph that line. Y-intercept is 5. Can you see the x and y axes? If not, here, I'll highlight them. There's the y-axis. There's the x-axis. And then now I'm going to graph this line. Remember, always start with the y-intercept. So start with 0, 5, 1, 2, 3, 4, 5. Boop, right there. And then now I'm going to count to get another point using the slope. So rise -3, that means you're going to go down 3. So down 1, 2, 3, and then run 1 to the right. Okay, so here we go. Let's graph this line. Oh no, that's not appropriate. Hold on, let's straighten this bad boy up. Oh, much better. Here's our line. Make sure you put arrows on it. Yes, it extends forever. Okay, now, all of the points on this line are part of the solution set to the inequality, but there are even more. And our job is to determine where exactly these lie. The line that we just graphed right now serves as a boundary between solutions to the inequality and non-solutions. We'll talk in a second about why I just graphed a solid line. Sometimes you're going to need to graph a dashed line. We'll get to that later. But basically, the equality, the line, is the boundary between solutions and non-solutions. So all the points on one side of the line are going to satisfy the inequality, and then all of the points on the other side will not. But how do we know which side is which? Well, one thing we can do is use a test point and test whether or not a point on one side of the line satisfies the inequality or not. What's a great point to test with? I love testing with 0, 0. You just got to make sure 0, 0 is not on the boundary. Is it? Nope. Here's 0, 0. So let's test with 0, 0 in the original inequality. Where is it? 3x plus y is greater than 5. So I want to see, is 0, 0 part of the solution set or not? So let's go ahead, substitute in 0 for x and 0 for y. I'm just going to have 0. Is 0 greater than or equal to 5? No, wait. So this is false. That means our test point 0, 0 was not part of the solution set. Okay, so that means all of the points that are part of the solution set are on the other side of the line over here. So I'm going to shade the side of the line that does not include 0, 0. So if 0, 0 or our test point was a solution, then every point on its side of the boundary is also a solution. So then I would have shaded the other side if I got a true statement. Either way, you'll still know which side to shade. If it's not a solution, shade the other side. If it is a solution, shade the side that includes it. Just make sure you're not using a test point that's actually on the boundary line, because that's not going to give you any information. Most of the time 0, 0 does a good job, but if your line goes through the origin, then you can't use it. And then just shade and indicate which side of the graph is part of the solution set, okay? All right, other thing we're going to talk about is whether or not the boundary line is solid or dashed. I promised you that, and so the time has come to do so. We're going to graph the solution set to x plus y is less than 4. So starting off, we're going to graph the boundary. Boundary line is x plus y equals 4. Notice in this case, we have a strict inequality. It's x plus y is less than 4, not less than or equal to. That means the boundary line will be dashed. Okay, this is a great time to just find the x and y intercepts and graph from there, since the equation, the linear equation, is in standard form. So just by looking, if you plugged in 0 for x, y would be 4. So I know the point 0, 4 is on the line. And then similarly, if you plug in 0 for y, x would be 4. Okay, so remember, a dotted or dashed line for inequalities that are strict, less than or greater than. Okay, let's get to graphing our line then. So we've got 0, 4, 1, 2, 3, 4, and 4, 0, 1, 2, 3, 4. And then now, I want a dashed line, and here we go. All right, look at that. And now we got to figure out which side to shade, okay? Can I test with 0, 0? We'll make sure it's not on the boundary line. No, it's not. There's 0, 0, minding his own business. Okay, so let's test 0, 0 in the original inequality, in x plus y is less than 4. So is 0 plus 0 less than 4? 0 is less than 4. Yeah, that's true. Okay. So that means I'm going to shade the side of the boundary line that includes 0, 0 this time. Okay. And it extends forever. So if you really just want to, get into it and color in, that's totally fine. Very nice. Probably a lot of you have to do your homework using some online system too. So they have little tools for you to click and fill in and shade the appropriate side. Okay, so test points are one way to figure out which side to shade. There is another way. It's a little more dangerous, guys, but I'm going to tell you about it, okay? If you're a careful mathematician, give it a go. Now, if the inequality is expressed in such a way that y is isolated, then we can determine which side to shade without using a test point. If our inequality is of the form y is less than mx plus b, or y is less than or equal to mx plus b, then we shade, what do you think? All of our y values need to be less than the line. We're going to shade below it. If our inequality is of the form y is greater than mx plus b, or y is greater than or equal to mx plus b, then we shade above the line. And if y is not isolated in the inequality, then you have two options, okay? So if y is not all by itself, here's what you got to do. Either carefully, please carefully isolate y, or don't and just use a test point. Why do I say carefully? Why am I so nervous for you? Remember, in inequalities, when you multiply or divide by a negative number, you have to flip the direction of the inequality. A lot of students forget to do that. So I just don't want you making a mistake because you're trying not to use a test point, okay? So figure out for yourself what the safest way is to proceed and do that, okay? The next one we'll do both ways for you to see, and then you guys can kind of decide what's working for you. So let's graph 3x minus 2y is greater than 6. Okay, so the boundary line, here we go. It is 3x minus 2y equals 6. Now you guys tell me, is it going to be dashed or solid? Good, it's going to be dashed. Write that down now before you forget. I like to write it right away because otherwise I get too excited and start graphing and then you don't even think about it. Okay. Method 1, let's do the test point. Okay, so I'm not going to isolate y or any of that. Let's get our intercepts. So x-intercept, if I plug in 0 for y, can you do it just by imagining? What do I mean by that? Like imagine this 2y is gone because you're plugging in 0 and then solve for x. You should be able to do it in your head. Right? Don't you get 2, 0? And then what about the y-intercept? Imagine you just plugged in 0 for x. So you have negative 2y equals 6. That means y would be negative 3. So 0, negative 3. Now I just have to plot those 2 points. So here's 2, 0. Here's 0, negative 3. And then I need a dashed line. And there's my boundary line. Okay, and then this method, I said we were going to use a test point. Can I test with 0, 0? Yes, I believe I can. Okay, so let's test 0, 0. In the original inequality, 3x minus 2y is greater than 6. So is 3 times 0 minus 2 times 0, is that greater than 6? No way, right? 0 is not greater than 6. That's false. So that means 0, 0, which is over here, is not part of the solution set. No, no, no. So we're going to shade the other side. And voila, that's it. There's your solution set. You don't write it out. You graph it. You go, look, there's infinitely many. It's so beautiful. Now, what if you wanted to isolate y? We're going to do it carefully. Here we go. So to begin, we're going to go back to 3x minus 2y is greater than 6. Okay. I want to get y by itself. So I'm going to move the 3x over to the other side, subtracting it. Now I have negative 2y is greater than negative 3x plus 6. And then to isolate y, I have to divide everything by negative 2. This is where you need to watch out. Here's the watch out eyes. And this means now you have y is less than positive 3/2 x minus 3. Whoo! So you can see by looking here, the slope is 3 over 2. Y-intercept is 0, negative 3. Okay, so if you want to graph it that way instead, this is totally appropriate. 1, 2, 3, 1, 2, x-axis, y-axis. So let's do it. Here's 0, negative 3. Up 3 over 2, right? The slope is up 3, run 2, dashed line, and then we have to decide where to shade. Well, I'm not going to use a test point since I wanted to show you the other option you have. Notice here, y is less than 3 halves x minus 3. So that tells me I need to shade below the line. All of the y values that satisfy the inequality are below or less than the boundary line. So you shade this side. For some really steep lines, sometimes it can be a little confusing for students to tell which one's above, which one's below. So if you want to use a test point always, that's fine with me. Just check with your instructor. You know, I have to tell you the truth. When I learned algebra, they didn't tell us about test points. We had to always just figure out above or below. And it was a little scary sometimes. So I'm happy these test points are out there. Okay, last idea, we're going to look at a system of linear inequalities. Now we know what systems of equations are. And so we can do something similar here where we consider more than one linear inequality at a time. So we have a system of them and we want to find a solution to the entire system. So what would it be? What would it look like? A solution to the system would be any ordered pair. So some ordered pair that makes all the inequalities true. It has to make everybody happy. So it makes all the inequalities true. All right, so let's look at an example here. We're going to graph the following system. X plus y is less than 1, and y is greater than x plus 2. So I'm going to go ahead and number them, and we'll consider each of them separately. So inequality 1, inequality 2. First, let's deal with inequality 1, which is x plus y is less than 1. Boundary equation would be x plus y is equal to 1. Is it dashed or solid? Good, it's going to be dashed. And since this one's in standard form, so pretty, let's just find the intercepts, x and y intercept. Can you do it in your head? Do you remember the little trick I showed you? X-intercept is going to be 1, 0. Y-intercept is going to be 0, 1. Bada bing, bada boom, let's graph it. So here's 0, 1, 1, 0. I need a dashed line. And then we got to figure out where to shade. Okay. Let's do a test point for this one. So test point, can we test 0, 0? Check, make sure it's not on the boundary. Yeah, we can totally use 0, 0. Okay, so let's test with 0, 0. So remember, we're plugging it into x plus y is less than 1. Is 0 plus 0 less than 1? Yep, that's a true statement. So that means 0, 0 is part of the solution set. Now, when I'm graphing a system of inequalities, your final answer is going to be where all of the shaded regions overlap. And it can get a little messy. So sometimes I just put arrows to remind me which way to shade if you don't want it to look too outrageous. Or if you just want to shade and then later erase, you can do that too. Okay? But your final answer, it should be clear where the overlap is for all the shaded regions. So sometimes it's good to clean it up afterwards. Okay, that's the first one. Now let's take care of the second inequality. Y is greater than x plus 2. Okay, love it. So we have here y is greater than x plus 2. Boundary is y equals x plus 2. Y is already isolated. So let's just go ahead, use slope and y-intercept. Slope is 1 over 1. Y-intercept, 0, 2. Okay, this one's also dashed, yes. Shame on me for not writing it out right away. Uh-oh. And here we go. 0, 2. And slope is 1. Be like that. And here we go. And then now let's see where to shade. So maybe you can tell maybe you can already tell without a test point, right? Because we have y is greater than x plus 2. So we should shade above the line, okay, which would be where? Over here, above, where the y values get larger. If you're not sure, you can still always use a test point. There's absolutely no problem with that. You can still test. Let's test with 0, 0. Is 0 greater than 0 plus 2? Is 0 greater than 2? No way, that's false. So that means 0, 0 is not part of the solution set. So again, you can see, all right, we got to shade the side, the side that doesn't include 0, 0. So can you see where the overlap is, where our final answer should be? Because it's looking like a hot mess right now, I think. Okay, clean this thing up. Right, get rid of all this. Make it nice and neat. The overlap was here and here. This whole region. Okay, so just make it clear. Ask your instructor how they would like you to proceed. Maybe not erase everything, but just make it very obvious where the overlap is. Okay, and that's your solution set right there. Beautiful. Now, last example, the graph of a system of linear inequalities can enclose a polygon, a region of the plane, and form a shape. And in these cases, the corners or vertices of the region are of interest. And later on, if you study more mathematics, you might learn about linear programming. And these vertices are important. So we're going to graph the following system and then find the coordinates of any vertices. And you notice it's gonna, the system, all of the lines, the boundary lines are going to enclose a polygon, a region in the plane. Okay, I say now's a good time, pause the video, see if you can graph these 3 inequalities on your own, and then push play, watch me do it, make sure you set up everything correctly. Since the start of it, you should be comfortable with doing, okay? Maybe just that last one, you'll need me to help you, but give it a go right now. Okay, so here we go. Let's go over the first one. We've got 2y minus x is less than or equal to 2. Okay, so the boundary is going to be 2y minus x equals 2. Is it going to be solid or dashed? Solid. Bravo. Okay. And then let's just get the x and y intercepts. So remember, imagine you're plugging in 0 for y. Then x is going to be negative 2. So we've got negative 2, 0. And if you plug in 0 for x, you have 2y is 2. So y is 1. Okay, let's plot that. So we've got negative 2, 0, 0, 1. This one's solid. Love it, love it. Whoop. And then let's test with 0, 0. Where's 0, 0? Over here, minding his own business. Let's test 0, 0. So is 0 minus 0 less than or equal to 2? Oh yeah, for sure. 0 is less than or equal to 2. Great. So that means we're going to shade below. I don't know, these arrows are looking ugly to me lately. Let's just do a couple gentle little highlights. Okay, that's reminding me which side to shade. Let's move on to inequality number 2. Number 2, we've got y is greater than or equal to 3x minus 4. So the boundary is going to be y equals 3x minus 4. Solid or dashed? Yes, solid. And in this case, y is isolated. So let's go ahead. The slope is 3, or 3 over 1. Y-intercept, 0, negative 4. So let's start off. Remember, you always graph the y-intercept first. 0, negative 4. 1, 2, 3, 4. And then the slope is 3, up 3 over 1. Up 3 over 1. And here's the line. We're going to shade above. How do I know that? Because y is greater than 3x minus 4. If that makes you too nervous, go ahead, use the test point. It's no problem. Let's test 0, 0. Is 0 greater than or equal to 0 minus 4? Is 0 greater than or equal to negative 4? Yeah, for sure. That's true. So that means you're going to shade the side that includes 0, 0. Okay. Which is above. It's just this one's a little steep, so sometimes you might get like nervous about it. Okay, last one. Maybe this one was a weird one for you. Did it make you nervous? We've got y is greater than or equal to negative 1. So boundary is y equals negative 1. It's going to be solid. Y equals negative 1 is a horizontal line. Do you remember when we graphed vertical and horizontal lines earlier? You could think of it like if it's in y equals mx plus b form, it's y equals 0x minus 1. So slope is 0. It's a flat line. Like you're on the treadmill, incline is 0, flat. Also, you could think x is missing. So x can be anything. It runs wild, parallel to the x-axis, but y is fixed at negative 1. So where is y negative 1? Y right here. Y is negative 1 right here. Why is that not straight? Please straighten up. There we go. And then where to shade? Just look at it. It says y is greater than negative 1. So we want all the y values where it's bigger than negative 1, above the line. Well, they're bigger over here. So can you see what region is enclosed, where the overlap is from this system? I'm excited. It's going to look so nice. It's this little triangle right here. Ooh, so cute. Okay. Lovely. Now, we have 3 vertices, right? Because it's a triangle. Let's label them. This one we'll call A. This one here is B. And this one here is C. Now, graphically, you can probably tell where they all are. So we'll write it out, and then I'll show you how you can confirm. Because in this case, I mean, they're all going to come out to be nice integers. But what if you have something where it intersects at like 2/7 and 1/3? I'll show you what to do, okay? So it looks like A has coordinates -4, -1. B has coordinates 2, 2. And C has coordinates 1, -1. Now, if you need to find them, because you can't tell from your graph, then this is what you could do. Say you want to find B. Okay, B right here. Well, B comes from the intersection of 3x minus 4 and that dark purple line was the first one, 2y minus x equals 2. So what you want to do, oh, hold on, let me write each of them separately. So B comes from y equals 3x minus 4, and where it intersects with 2y minus x equals 2. All you need to do is solve this system, so we could use substitution. Substitute in 3x minus 4 for y, if you want. And then we're going to have 2 times 3x minus 4 minus x equals 2. This is going to give us 6x minus 8 minus x is 2. So then I have 5x minus 8, let's move it over, equals 10. So x equals 2. And then you can go back, figure out the y coordinate. Y equals 3 times 2 minus 4. 6 minus 4 is 2. So that point is 2, 2, like we saw from the graph. So again, how did I know which 2 boundary lines to set equal to each other? Well, you just look at the graph that you drew, right? So notice B comes from the intersection from the first and second boundaries that we graphed, set them, make a system from those 2 boundary lines, solve either by substitution or elimination as you've previously studied, and then you can find the ordered pair. If your graph is really nice, you can read off of it, but of course you're kind of guessing a little bit, right? So make sure you know how to algebraically find it as well. And that concludes the video. So be sure to subscribe, give this video a thumbs up, share it with your classmates and friends, and you can always message me or comment and let me know what other topics or videos you'd like to see next. We're going to get into a lot more algebra coming up.